Today we're going to talk about big idea number 1. How does the structure of an atom determine the physical and chemical properties of an element? And go over learning target number 2, describing the structure of an atom and what it will do to become stable. And as well, learning target number 3, describing what isotopes are and calculating the average atomic mass of an element. You probably remember from previous science classes that atoms are made up of 3 different parts called subatomic particles. One part is called a proton. The short form, instead of writing the word proton all the time, is just writing a P with a positive sign. Protons have a 1 plus positive charge and have a mass of 1 atomic mass unit. Atomic mass units are represented by the symbol U. Protons are found in the nucleus of an atom, and you can determine how much each element has by looking at the atomic number on the periodic table. Neutrons are also found in the nucleus. They are neutrally charged, and they're there to prevent the positive protons from repelling each other. Remember, like charges repel. So neutrons actually form a bond with protons to keep the nucleus together. If they weren't there, atoms wouldn't exist. They also have a mass of 1 atomic mass unit, and you figure out how many neutrons are in an element by taking the atomic mass and subtracting the atomic number found on the periodic table. Here's an example for figuring out the neutrons for fluorine. The last subatomic particle are known as electrons, short form E-. They're negatively charged, and they're so small that we really don't take their mass into consideration. So often they're defined as 0 atomic mass units. Electrons are found outside of the nucleus of the atom, orbiting in shells. The number of electrons that an atom has is dictated by the element's atomic number, same as the protons. Now this number can change when an element does chemical reactions, but if it's an atom, it has the same number of electrons as the atomic number. In terms of placing electrons, you can put 2 electrons in the first shell and 8 in any other shell. Scientists have noticed that not all atoms of the same element have the exact same mass. These are known as isotopes. They do have the same number of protons in the nucleus. That's what makes an element an element. For example, every carbon atom has 6 protons in it, no matter what. If it doesn't have 6, it's not a carbon. But isotopes have a different number of neutrons, giving the atom a different weight. Each element on the periodic table has at least 2 isotopes that are naturally occurring. Here are some examples for carbon. Carbon 12, 13, and 14. Those numbers indicate how much the atom weighs. Pause the video here and figure out how many protons, electrons, and neutrons are in each isotope of carbon. Here are the answers. Notice that the number of protons and electrons for each of the carbon isotopes are exactly the same. They're all 6. But what makes them different is the number of neutrons. Isotopes are identified by using a piece of equipment known as a mass spectrometer. What it does is it's an instrument that measures the mass of atoms by passing the sample through a magnet, and depending on how heavy that atom is, it will bend a different amount. Have a look on page 281 of your textbook for more information of how this device works. If you run a sample of an element through a mass spec, it won't just show you the different masses of your isotopes, it also shows you how much of each you have. That's known as its isotopic abundance. So it's the relative amount of a given isotope of an element that exists in nature expressed as a percentage. So if we're looking at carbon, 98.9% of all carbon atoms in nature are actually carbon-12. Only 1.1% are carbon-13, and less than 0.1% is carbon-14. Isotopes are not usually found in equal amounts. Because of this, the question becomes, what mass do we put on the periodic table for an element? What we do is we find the weighted average of all of the isotopes and take into account their different abundances. Here's the equation to do this. The average equals the abundance of the isotope times the mass of the isotope plus the abundance times the mass of all the other isotopes put together. Now there is a trick to this equation. When you sum in your numbers, you have to put in your abundances as decimals, not as percentages. Let's try an example. Lithium has two isotopes, one that weighs roughly 6, one that weighs roughly 7. If we were doing a straight average, then lithium would be reported as having a mass of 6.5 on the periodic table. We would just take these two masses, add them together, divide them by 2. But that wouldn't take into account that most of the lithium out there is lithium-7. So we have to use the weighted average equation to find the average mass of a lithium atom. My average would equal my abundance of my first isotope, but I would take my 7.42% and divide it by 100, times the mass of my first isotope, plus the abundance of my second isotope expressed as a decimal, times the mass of that isotope as well, I would punch that in my calculator, and the average mass of a lithium atom is 6.9408 atomic mass units. Try out the second example and calculate the average atomic mass for silver using the information in this chart. Pause the video and see if you get the correct answer of 107.9 U's. Scientists have also noticed that some isotopes are not stable. That means that they will cause a nuclear reaction and explode and release energy. These are known as radioisotopes. Again, these isotopes are naturally occurring. The reason why they decay is because the forces between the protons and the neutrons are not properly balanced in the nucleus. That means they either have too many protons or too many neutrons so that the nucleus can't stay together. It does not mean that a stable isotope needs to have the same number of protons and neutrons. For example, we've got carbon-14. It's used to date things in archaeology. When you're alive, natural carbon-14 gets incorporated into your body. As it explodes, your body heals that by replacing it with another carbon atom. We know how long it takes for carbon-14 to explode and how fast it does. When you die, your body stops replacing it. So by looking at how much carbon-14 a dead body has, we can backtrack and figure out how long ago that it died. Another example is uranium-238. It explodes, and we actually are able to collect that energy that's released in a nuclear reactor to create electricity. Finally, let's review how we represent atoms using diagrams. There's two different diagrams that you can use. The first is known as a Bohr-Rutherford diagram. A Bohr-Rutherford diagram shows all the pieces, the subatomic particles of an element. For example, let's look at sodium. Its atomic number 11 and has a mass number of 22.99. Let's round that to 23. In order to do a Bohr diagram, we show how many protons are in the nucleus, that's given to us by the atomic number, and how many neutrons are in the nucleus. That is the mass number minus the atomic number. And then we show the electrons orbiting the nucleus in shells. Now I have 11 electrons, 2 can fit in the first shell, 8 can fit in the next shell, and that leaves 1 in the other shell. Now depending on what teacher you had, their Bohr diagram might have looked a little bit different. Some teachers like to draw the whole circle and represent the electrons by dots. This is a fast, short form version of a Bohr diagram. Lewis or electron dot diagrams are what we're going to be doing mostly in this course. It shows the symbol of the element, and it puts a dot for every valence electron the atom has. The valence electrons are the electrons in the outermost shell. Sodium has 1 valence electron. I know that from doing a Bohr diagram or counting out. Or a trick is by looking at the group number. Sodium is in group number 1. That means it has 1 valence electron. If you're doing a diagram that has more than 4 electrons, what you want to do is follow the clock method. So for example, if we have a look at chlorine, chlorine's in group 17. In order to figure out the number of valence electrons, I just take the second digit, 7. I start drawing my dots by starting at 12 o'clock at the top of the symbol, and then go around spreading the electrons out to the 4 sides before I go back and pair. Now, atoms that have lost or gained electrons to become stable are called ions. And atoms either want 8 or none in their outer shell. For example, if we're having a look at sodium again, sodium has 1 valence electron. It has a choice. It could either gain 7 or lose 1. Atoms will always do the least amount of work. So sodium will lose that valence electron and become what's called a cation, or a positively charged ion. To show that in a Lewis dot diagram, we would do this. Here's the Lewis dot diagram for the sodium atom. We would show this electron going away somewhere else, and the sodium would now have a 1 positive charge. Atoms are positive for every electron that they lose. So if they lose 1 electron, 1 plus, 2 electrons, 2 positive. It's a little counterintuitive. Because you're giving away electrons which are negative, what's left over is positive. Let's have a look at chlorine. Chlorine has 7 valence electrons, in our Lewis dot diagram here, it has a choice. It could gain 1 electron or lose 7. It's much easier to gain 1. And when you gain an electron, you become negatively charged, which is called an anion. We would draw the anion diagram for chlorine like this. We would start off with our 7 dots, and then we would say we would gain an electron from somewhere else. We could either use a different color for that electron, or we could say, hey, I have an electron going in there. And then we would put a 1 minus charge on the chlorine. Try out the homework worksheet.